Yeah, we can get started. Okay, so yeah, thanks everyone for coming. So today we have Dan Foreman-Mackey, who is a living legend of kind of open source software for science. So he has some famous packages for MCMC. You might have heard of MC, EMCEE. That's Dan. He works on exoplanets, many other things. He's a great resource for like open source communities, software design. And today we get to hear from him on Gaussian processes, which he also works on. So take it away, Dan.
Thanks. All right. Yeah, thanks, Miles. I'm going to try putting this up here and see if that kind of does the trick. Yeah, if people online can't hear me, let me know, because I'm going to be doing lots of wandering around. So I have, it's a little bit all over the place. I love this topic of Gaussian processes. So I have some slides, I have some stuff I'm going to do on the board, and I'm going to do some live coding just to be, what could possibly go wrong. So I guess who here, because I don't really know very much about where we are right now. Who here knows about Gaussian processes? Okay, cool. Who has used Gaussian processes before? Okay, good, perfect. Okay, this is great. I think I'll have useful things for everyone, hopefully. But yeah, just interrupt me as we go, and if you have any questions, and this is the kind of thing where I've almost certainly hit exactly the wrong length of time and stuff like that. So, whatever. Okay, so yeah, I don't know anything about machine learning, but I do write a lot of code. Like Miles mentioned, that's been a big part of my work for a long time. And in particular, I write a lot of Gaussian process codes. So my most recent one is TinyGP, and that's one of the ones that we're going to live code with a little bit later on today. But I have various other Gaussian process libraries that I've written in Python over the years, and so that's sort of where part of my credibility for giving this lecture comes from. These are my coordinates online. If you have any questions afterwards, or things that you want to chat about, please do get in touch. I'm always very keen to chat about projects. Good. Okay, so I wanted to start. So I know that this is like a machine learning thing. I said I don't know very much about machine learning, and in particular, I generally sort of come at Gaussian processes from a different direction than a lot of machine learning folks would. So I'm gonna sort of introduce Gaussian processes in maybe like a slightly strange context, but I want to start by talking about how I first got interested in Gaussian processes, sort of so that we have some concrete example to think about as we go. So I've spent much of my career studying transiting exoplanets. And so this is a time series of the brightness of a star. These are real data taken by the Kepler spacecraft. And the blue line that you see is a model based on physics and geometry for what it looks like when a planet transits in front of its star. And then the black points are data, and they have cute little error bars on them. Okay, and so I've spent a lot of my career sort of trying to discover these kinds of signals and characterize, fit models like this blue curve that has a lot of parameters to try to learn things about the physical systems. Now, of course, I said that these are real data, but it's not quite true. If I zoom out and show you, this is what the real data actually look like. And in fact, this is actually a pretty high signal to noise case. So you can see the transits here in the top are aligned with the ones down here, but there's also a lot of other stuff going on in here. And while I have a very good physical model for the transit itself, like this blue line down here, I have a very good model for that. It's much harder to write down like a first principles model for the variability of the star. So there are lots of sort of physical things going on here. A star is a boiling ball of gas that's rotating. It has spots, it has flares, it has all sorts of other things going on. There are also instrumental effects. So the spacecraft is changing temperature and changing focus and these kinds of things. So there are all sorts of things going on in here that can be quite hard to model from first principles. And so the blue line that I've drawn through here is a Gaussian process model that I use to capture that variability without having to specify it deterministically. And we'll talk a little bit more about what that means as we go. And this gives me a way to characterize the planet that I care about while taking into account the fact that there's lots of other signals going on in the data. Good. Okay, so this is where I started with Gaussian processes, and there are lots of other use cases that we'll talk about as we go forward, but I just wanted to set this context because I'll use language that fits thinking about data analysis this way. Good. Okay, so now I'm going to move to the board and give a little bit of the mathematical foundation of Gaussian processes. Good. Let me see. What I'm going to get my notes and some of these. Now I don't know how the mics do with me being over here, but unfortunately I'm always going to be standing on the wrong side of the board. Whatever. Well, let us know online if there are any issues. Okay, so I think about, like I showed here, the context that I think about Gaussian processes a lot of the time is in the context of probabilistic data analysis. So I'm trying to fit some model to data, and the Gaussian process is an element in that fit. And so let's think a little bit about how you fit data. What is the process of fitting data? I'm going to draw, sort of similar to my motivating example from before. I have some time series, has some error bars on it, right? Okay, whatever, it looks like that. And then I have some model that I want to fit to these data. And in this case, it looks something like this. And that has some parameters to it, like, the depth and the duration of the signal and things like that. It has some parameters to it. And so let's call that f of x parameterized by some parameters theta. That's maybe too small. Let me write it a little bigger. F of x parameterized by theta. Okay. Awesome. Yeah, good idea. Great work. Good. And can you guys see that over there too? Yeah, okay. Good. Okay, and so I have this function I want to fit for theta. What do? We need to write down some objective. Say, for example, we might write down the weighted residuals. So we have some observed y(n)s minus our function evaluated at xn squared. That's yeah.
Yeah, you won't walk it.
Awesome, thank you. Weighted by the error bars, for example, summed over n. So this gives us some loss function for theta that we can minimize to find, to make some estimate for theta. Is anyone here an astronomer? Okay, so in astronomy, we often call this chi-squared. I don't know if other fields do that, but this weighted least squares, right? This is an objective. Now, another way of getting to this same result is you might you might think about the sampling distribution for a single point right here. So some point yn is equal to our model evaluated at xn plus some noise, some error term here. Let's call that epsilon n, where epsilon n is drawn from a Gaussian with mean 0 and variance sigma n squared. So this defines a different, this defines a probabilistic model for each data point, and we can write down the likelihood function that corresponds to this right here by looking up the function for a Gaussian on Wikipedia. And so that gives us the probability of yn given theta is equal to, I don't have to look it up on Wikipedia because I've written this on the board so many times, but it looks something like this. Good. Okay, so this is the formula for a Gaussian. We normally don't like to work with probabilities directly. It's better often to work in the log because they tend to be, the probabilities are always 0 identically. And so let's take the log of this. Log of this. That lets us get rid of this exponential and it puts a log here. Good, and then suddenly this is starting to look interesting, right? This quantity right here is the same as this right here, and we're back to weighted least squares, right? So this right here is a constant if our sigmas are known. This thing is -1/2 times our loss function up here. So maximizing the likelihood is equivalent to minimizing this loss function up here for theta. Good. Okay. So this might be review, but this is a sort of a useful place to come at all of this. Good. Okay, any questions about this? Great. One brief aside that I wanted to bring up here. Oh, I guess one thing that I should say is that I've actually only written it for one data point here. We would sum over all the data points or take the product before taking the log over all of the data points to get the same result up here. So let's do that. So summing this one, or no, let's just do it.
We're assuming independence.
Yeah, well, we're going to get to that in just a second. Good. So we have a sum over n of this whole thing. Great. Let's come back to the independence point in just a second, because that's sort of the whole story. But I wanted to give a brief aside here. So this is the case where we've assumed that we know the error bars. So someone has handed us some estimate of the uncertainties that we're believing. So we're allowing those uncertainties to be different on every point, but some process gave us some estimate for these uncertainties. A lot of the time in real life, we don't actually have a very good, like maybe someone gave us in our data table a list of uncertainties, but they're often not very good, or maybe someone didn't even produce that. And so, yeah, go ahead.
There was the error bars in X.
Are there error bars in X? Yeah, so I'm going to assume for now and for the rest of what we talk about today that there are no error bars in X. So for example, in my use case, I measure the times when my observations are taken perfectly to essentially infinite precision. And that is the use case that we're going to talk about today. Error bars in X become quite a bit trickier. So we're assuming that there are no error bars in X. We know those perfectly, but we also know the sigmas perfectly, and then that's why this term becomes a constant. Now, so what I was saying that a lot of the time you don't actually know that very well. So in fact, you have to fit for the noise model. So you want to fit for the variance, and you can do that if, let's say, we we just replace our sigma n's by, say, just a parameter s, or maybe if we were handed core estimates of our error bars, we might fit for something like that. And now s is a model parameter. Now we can't do that if we write our model this way, right? Because if we fit for s using this objective function, we would end up with some value like this, and to minimize that quantity, we would set s to infinity, right? So the best fit value for s under this loss function is infinity. But in this one down here, if we're fitting for s, we increase s over here, the sort of goodness of fit gets better, but this normalization constant gets worse and worse. So these two terms are going to be trading off from each other inside of your optimization, and it's only going to make your value of s as large as it needs to be to properly explain the data. And so that's why it's really useful to include this term when you write down your likelihood for a model like this. And whenever I fit models to data, I always fit for that error bar, because it never really hurts to add this in. Like I said, it'll set s to 0 if it's not necessary to explain the data. Good. Okay. So all good. Now, the point about independence is where we're going to move now. So the other assumption that I made here was that each of the data points was independent. And in order to show that, I'm going to rewrite this equation in a different way, which might seem a little bit tedious, but bear with me. I'm going to erase these lines here. Good. Okay. So another way of writing this equation right here, in the case of the full data set, is as a matrix equation. So we can write log p of all of our y's given theta as minus 1/2 r, I'll define things in a second here, okay, so this is the matrix version of what I wrote before. These r's are vectors, the C is a matrix, and the nth entry in R is just yn minus f of xn and theta. So it's just the residual vector. So you just take the difference between your mean model and the data, that gives you R. And then C is a diagonal matrix with the sigma n's squared along the diagonal, sigma 1. And zeros everywhere off diagonal. So if you squint a little bit, maybe you can also just trust me. If you work through these versions of these expressions here, in this, you reduce down to exactly this. So these two expressions are identical versions of exactly the same thing. Now, and the reason why it's useful to think about this is because this is where we start to get Gaussian processes. But the important point here is that the zeros off diagonal are what's represented by this assumption of independence. So what we're saying is that there's no covariance between neighboring data points. The only stochastic part of our model is along the diagonal. So that means that there's some error bar on each point, but there's no covariance between the other points. And so if we do want to encode some correlation between the different between different times, in my time series example, we want to start putting elements in the off-diagonal entries of this matrix. And that's what a Gaussian process is. Cool. Okay, so we could just, put a free parameter in every entry in this matrix. The matrix has to be symmetric, has to be positive definite. So there's some constraints on what's required for those parameters, but essentially you could have n squared parameters where n is the size of your data set and just fit for every entry in this matrix. But that's in general going to be fairly poorly constrained and perhaps intractable. And so the approach that we usually take in Gaussian processes is the following. I'm going to straight over here for a second. Good. So we take our matrix C and we replace it by something called K, for reasons that will come clear in a second. And the nth element of K we write as I'll come back to that in a second. Another way of writing this matrix is the following. So using the Kronecker delta, this is a diagonal matrix, is how you would specify that. So it has the sigmas along the diagonal. So in the context of Gaussian processes, what we do is we introduce some function that describes the covariance between two data points, xn and xm, and it's parameterized by some parameters alpha. Okay, and then, bear with me. And then given that, this gives us a procedure for filling our entire matrix K, and then we could evaluate this log probability over here. And I'm just going to rewrite this as K. This is K. Okay. And then that gives us an objective function for both theta and alpha. And that gives us a way of fitting for our model parameters theta that we care about, taking into account the fact that there's some correlated structure in the data. All right. So for example, the case that I talked about earlier here where we were fitting for our S is one example of what K could be. So K could just be S squared and then Kronecker delta, so a diagonal matrix of S squared along the diagonal. But in general, that's not going to introduce any correlated structure because it's still diagonal. So instead, we want to put some something a little bit more flexible in there. And so a common thing to do would be something like, say, say something like this here. So this now says that, so this is another Gaussian. It's get Gaussians all the way down. I'll talk about that in a second, but so this is an example of a covariance function that has two parameters. It has an amplitude, so it's like how correlated are nearby data points, and then some length scale. And so A has units of y, and L has units of x. And so that can be useful to think about it is that you're now saying that there's some correlation length in your data that captures how long does it take in time before you forget about the state you were in. And then this parameter A that describes how correlated your data are. There are lots of other examples of these functions, and I'll talk a little bit more about that later. But this is the basic idea of a Gaussian process. Before I go on, I want to show a couple of slides just to give some sense of this. So I think this is so lots to say. So here is the function k. It's often called a kernel function or a covariance function or something like that. And this is the value of k. So here we've set a equal to 1 and L equal to 1, right? And what I'm showing on the top here are some prior samples from the Gaussian process. And so let's talk a little bit about what that means. So this equation right here defines a probability distribution over y's, right? So conditioned on some setting of theta and alpha and x, this gives us some way of generating samples of y. And this is a multivariate Gaussian. This is the equation for an n-dimensional Gaussian. And that's the reason why this is called a Gaussian process, is the fact that this equation is a Gaussian. And what we can do is we can choose some setting for alpha and theta. Here we've set theta just equal to 0. And we can generate samples of y and plot them and see what they look like. So for different random seeds, I would get a different line on this top plot. So you'll see a lot of the time in the Gaussian process literature that Gaussian processes put a prior over functions. And that's sort of what they're talking about here, is that for some setting of this covariance function, I could get these different samples that have similar properties. They have similar covariance properties, so they have about this, they have the same correlation length and similar amplitude in their variability, but they're very different realizations of the process. And we can change the parameters. So if we make the L longer, then we get smoother or longer correlation lengths. We can make it smaller, get a lot more structure. And if we make A much larger, then we get higher amplitude variability. And so that's just to sort of give you a sense for the kinds of things that's possible with these functions. Any questions at this point? Yeah.
How do you actually sample a curve from this? Because it's defined with a discrete number of points.
Great. Yeah. So the way that I did that was I put down 1,000 x coordinates right here. And then I populated that k matrix for those 1,000 x values. And I passed it to numpy random.multivariate normal with that k as the matrix. So this is a discrete representation of the continuous underlying function.
So an L would like shape that width of a kernel function?
Right, yeah. So here, this is L equals 1. This is L equals 2. And the x scale is the same between those two. So you can see how it sort of qualitatively changes the types of functions that you generate. Does that answer? Yeah. Or if you make it smaller, you get something like that. You can see that even this very simple, 2-parameter covariance function has a lot of flexibility in the types of functions that it can capture. But not everything. So one thing that's really important is that all of these are smooth, right? These are discrete representations of the function, but they are smooth functions here, and not all Gaussian processes are. But that's one particular thing that we're imposing on our underlying function by choosing this type of covariance function. Any other questions? Cool. Okay. So the last thing, I had one more thing I wanted to write on the board. What was it? Good. Oh yeah. So the last thing I wanted to say was, so first of all, I've been talking about one-dimensional Gaussian processes because that's what I'm sort of most familiar with. Like, I do a lot of time series analysis, and so that's natural. But you can rewrite all of these things with vector inputs. So your x's can be higher dimensional than 1, and you can still write down multivariate covariance functions. But sometimes the structure is a little bit harder to reason about. But then the last thing I wanted to say was, one of the reasons why people in machine learning really like Gaussian processes is because their conditional distributions are also tractable. So what I mean there is when, let's say I want to predict, so conditioned on my observations y, I want to predict what I would expect the star to be doing at some time in the future, say in this example, or in other case, other processes, the stock market or something, I want to predict it in the future. And through the magic of Gaussians, it turns out that we can write down a closed form expression for what those predictive distributions are. Just for completeness, I'm going to write them down here. Actually, I'll do it over here. So let's say I want to predict the probability of some new y star, which is measured at some new x star, conditioned on the observations that I have so far and some setting of all of my parameters. It turns out that this thing is a Gaussian with some mean mu and some covariance sigma. So that's the thing. So this is the wonderful thing about Gaussians, is that the marginals and projections and slices and everything you do on a Gaussian produces a new Gaussian. And we can write down what these mu and sigmas are. Although I might not. It's not very enlightening to show what they are. No, I will. I lied. So our mu is going to be f evaluated at y star. Oh, sorry, x star. Plus k star transpose k inverse y minus, well, let's just write r. From before. Good. So that's our mean for our prediction, and then our covariance is star minus k star transpose k inverse k star. Okay, so k star is the covariance between your predicting point x star and all your observations. So when you're predicting, you need to remember the locations of where all of your observations were measured. That's a big thing. And then K star star is just the covariance of the predicted point against itself. And this, the way I've written this actually generalizes to the case of vector prediction. So if you have multiple x's where you're predicting, you would write down the same equations. Good. Okay. So that is a whirlwind tour to the mathematical framework that is Gaussian processes. And so I wanted to move on now to some sort of more practical discussion of how you would use these things in real life. Any questions before we do that? Yes.
So I have a similar question to the one I asked before. So
yep.
I'm basically trying to get intuition for why it looks smooth, like a sample of a curve in a Gaussian process. Like, why is it smooth? Because I can see how you evaluate the kernel for like new points, but the samples, like when you draw samples, you draw individual points.
That's right.
So, why is it smoothly connected, each sample of the Gaussian process?
Oh, right. So the important point is that so it's sort of the same in this and in the conditional distribution. And the reason for that is that if I independently drew all of my points, then absolutely it wouldn't look smooth, right? It would jump between different lines here. But the fact that I'm generating a multivariate Gaussian and I'm plotting it with respect to the coordinate that I use to compute my covariance, that's the thing that makes these realizations smooth. Right, so it's the fact that we've actually populated the 1,000 by 1,000 covariance matrix, and we're generating a single realization of the n-dimensional vector, the 1,000-dimensional vector from that. And sort of a little bit by magic, those points are going to be smoothly connectable under this choice of kernel.
Okay.
It's a great question. Yeah. Anything else? Yeah.
So I guess in this image, did you say again what you're plotting on top of it?
Good. Yeah. So this is
Like an axis, I guess.
Oh yeah. So the axes are y and x, like I've written over here. So in this case, I'm not doing the exoplanet model. I'm just doing the case where I've set the mean function to 0. So f of theta is just 0 everywhere. And then what I'm doing is I'm generating samples from this probability distribution over y, but my y, it's useful to think about it as an n-dimensional vector, and so each realization of that n-dimensional vector is being plotted as one line on the top here. And we'll see some more examples of this later on. Anything else? Great. Okay, so I wanted to talk now, and yeah, feel free to go back to other topics later if we want. Good. So Gaussian processes are awesome, and anywhere where you're using some weighted least squares, you could be using and should be using a Gaussian process, right? All the time. This is what I've been telling all of my astronomy colleagues, is that everyone should just be using Gaussian processes all the time, which is, sort of true. But there are various problems. And so I want to talk about the practicalities of using these in the real world. So I sort of glossed over decisions about the choice of covariance function that we make. Like that, in fact, is sort of, that's one of the fundamental design decisions that you make. And then the big one that I'm going to talk about is computational cost. But let's start with the choice of covariance function. And I'm not going to talk about this in very much detail because I don't actually think it's as big of a problem as people think it is. So in my work, a lot of the time, I have physically motivated choices that I can make. So I know something about the timescales in the problem, or the autocorrelation or power spectrum of my noise, things like that. I can make informed decisions that are informed by my understanding of physics in my choices. If that's not the case, at the end of the day, this is just a modeling decision in the same way that any other choice of model components are, right? So you are required to specify the function that you're fitting, and if you don't have a sort of first principles argument for why you should use a particular choice, what do? You do some sort of model comparison or something like that. And here we just have a log likelihood function that we can incorporate into any sort of model checking, model validation framework that already exists. Yes?
Even if you do have some information about what the kernel should be, it's not always that it will be a valid.
It's not always what's right?
Valid kernel, in fact, it won't satisfy it. So, is there a principled way to actually do?
Yeah, absolutely. So there are so like a lot of stochastic ODEs, for example, can generate a valid kernel that you can calculate from first principles and things like that. So there are lots of examples of like Gaussian processes that are good representations of that satisfy all of those things. But you're absolutely right that if I sort of had some like numerical estimate of the power spectrum of my noise or something like that, I couldn't necessarily just plug that into a Gaussian process and use that. And that's totally true. And so the approach that I would normally take would be trying to like come up with an approximation to that by using a basis of valid kernels that you can add and multiply to generate something that does a good job of capturing the key features of your physical process. And is flexible enough to sort of have that capacity that you need, but it's not super well defined. What I'm saying, there's a lot of in between there, right, where you have motivation for the choices that you're making, but you still want to do model validation using that choice of basis. Great question. Okay. And so I'm not going to talk about details, but things like cross-validation, Bayesian evidence, et cetera, are things that you may want to do when specifying your choice of kernel. Another thing that I often do is in my work, I'm normally most interested in theta, so like the parameters of the mean function rather than the actual GP model itself. And so in those cases, I can demonstrate that my results are not sensitive to different choices that I make in the covariance function that I choose. Or if you're most interested in having good predictions, you can just check the predictive performance of your model on held out data, things like that, and choose the model that does the best job there. Good. Okay, so all of that is true as long as you can evaluate your model in finite time, and these types of model checking activities require many evaluations of your model because you're normally doing some sort of nonlinear optimization or MCMC or something like that behind the scenes, and so that means that at the end, you're going to end up evaluating your Gaussian process model, billions of times or something, and depends on the context. But and the reason why lots of people shy away from Gaussian processes is because in fact they're very expensive. So this is rewriting what I have on the board over there, and the key things that I wanted to point out here are the fact that we have to solve this linear system. So we have to like invert K. In fact, we don't most of the time. We would solve a linear system here and compute its determinant. And that operation scales as the cube of the number of data points that you have. it's the cube of the size of your matrix, which is set by the number of data points that you have. So, if you double the amount of data you have 8 times more expensive calculation of this log probability. Similarly, I think, here. So similarly in the prediction, the expensive parts are also doing this linear solve. You see, we have this inverse of k again. And so in both cases, that scaling is going to be the thing that really makes us, worry about the general performance of this. And in fact, you can. I did an experiment on one of the Flatiron computers, sort of looking at the empirical computational scaling of using a Python package, and you can see that asymptotically it does scale as the cube of the size of the data set. And there's some Python overhead for small data sets over here. Good. Okay, so this doesn't look so bad. If you have 1,000 data points, it takes less than a second to evaluate that log probability once. Not such a big deal. We have lots of computers. It's not so bad. But if you have more data, so most of the problems I work on have much more than 1,000 data points and training points, for example. And so for the kinds of things I was working on, naive calculation of a Gaussian process would take 3 weeks on a supercomputer to evaluate one function call. This n-cube scaling really, really hurts. And so that's a big problem. Okay. So what are some things that we can do about that? Because people do use Gaussian processes for big data sets. So here's some of the things that I thought of that are possible solutions. And I'm not going to talk in too much detail about any of them, but I just wanted to sort of give the overview. So you can get a pretty long way with just investing in hardware. And so, for example, there's been a lot of work on GPU accelerated linear algebra. And that was actually something that I meant to mention here. By writing it this way, what I wanted to show was that this is a computational linear algebra problem, right? So I don't know if you're familiar, this @ symbol is the Python operator for matrix multiplication. And the point I was making here was that at its core, Gaussian processes are a computational linear algebra problem. And so we might be able to take advantage of some of the work that's been done on GPU accelerated linear algebra or parallelized linear algebra, those kinds of things. It turns out that there are lots of cases where, in fact, there's a lot of structure in that matrix K. So for example, if you have evenly sampled data, so if you have a time series that records data every second or something like that, that matrix has particular structure. It's often toplets, and there's lots of fast things that you can do when working with those matrices. And in fact, a lot of these stochastic ODEs also fall into the same state of having a lot of structure in the matrix that you can take advantage of. And so if you get lucky and you're working with a problem where you can use that structure, that can go a long way. I'll mention that a little bit later. The other thing you can do is there's also a lot of work in approximate linear algebra. So we don't actually need to solve this equation to machine precision because in fact, our constraints on the parameters are not very precise a lot of the time. And so it's okay to have sort of noisy estimates of this loss function. And so there's a huge amount of work on approximate schemes, and then there are lots of other things that I sweep under, etc. Okay, so let's say a little bit more about each of these. I already mentioned GPU acceleration and parallelized. And a lot of these benefit from algorithmic approaches that use iterative methods instead of direct methods. So like if you go into Python and say like linalg.solve or something like that, that solves a linear system, and it does it through a specialized algorithm for solving linear systems. A lot of the time you can benefit from using an iterative method like conjugate gradient that only ever takes matrix vector products. And so most of the like accelerated methods that people are using benefit from that type of approach. So a completely different approach to solving the linear algebra. And it's much easier to parallelize a matrix vector product than it is solve. Good. I mentioned a lot of these things already. Oh yeah, so uniformly sampled data is a good one. Kronecker products are if your data live in a tensor product grid. So if you have like time in one axis and like temperature or like latitude or something in the other dimension, and you have measurements at all times at all latitudes, then your matrix has this type of structure called Kronecker structure, and there's lots of fun things you can do with that. I'm not going to talk about it in too much detail. Another one that people are often drawn to is sparsity. So remember that I showed way back here, over here. In fact, most of the entries in our matrix are nearly identically zero, right? If your L is short compared to the baseline of your data, as that means that most of the entries in your matrix are zero, and so you might be able to exploit sparse linear algebra schemes. I haven't had very much success with that in the problems that I work on, but I think it's an interesting thing to think about, depending on the, like, there are just like libraries that exist for sparse linear algebra that you might be able to benefit from for solving this. And then my favorite kind is something called quasi-separable matrices, which is what I've been spending all of my life working on these days. But I'm not really going to talk about that at all. But it's a type of matrix structure that is broadly applicable and very, very fast. Oh yeah, so like this, the standard approximate linear algebra approach in Gaussian processes is actually just to like take a subset of your data and evaluate the model just on those data, and then there are corrections that you can do to take that into account. That's actually great because n cubed helps you if you're reducing the size of your data by a huge amount, right? But also it lowers the precision of your results. But that might be okay. And then there are lots of other things that you can do in this space. Good. I'm not going to talk about any of those things. Okay, so here's the plot that I showed you before. I've worked a lot on building different Gaussian process codes, like I talked about before, and here I've made a plot of a bunch of my different codes running in different environments with different choices and stuff like that cover the range of bases that I talked about. And you can see that you get dramatically different performance. So for example, so this purple line right here is just a naive algorithm that I'm just running it on a beefy GPU, right? And so you get a huge benefit for like moderate systems compared to the blue line, which is the one from before, but it does scale as n cubed eventually. So it's not going to, just like running a Cholesky factorization on a GPU isn't going to save you across the board. The orange line is an approximate linear algebra method, and so it has good scaling, n log squared n, but it is very low accuracy in the evaluations of the function. And then this last one is my quasi-separable matrices that I'm way into. And it's super fast, but it is very restricted on the type of problems that it can solve. So it basically only works on 1D problems with particular kernel functions. But it's super fast if you can use it. Yeah.
What is HODLR?
Yeah, so that's the hierarchical off-diagonal low-rank approximation, and so it's a sort of scheme for approximately solving linear systems when you have smooth matrices, where smooth is in air quotes. Good. So yeah, this was just, and I felt comfortable showing this because I'm competing my own codes against each other, and I'm not, there are lots of other codes that you might use that may be better or worse depending on how well you know how to use them. Okay, so let's talk about implementation. So all of this is pretty straightforward, in fact. So here's a complete implementation of Gaussian processes in Python. I think I once wrote this in a tweet even before they made the character count longer. And this is the whole thing. You can make it slightly better by, I reduced the constant a little bit in this version. This is a slightly more intelligent implementation and is in fact more or less exactly the one that I used for the first experiment that I showed, okay? So this is cool. This is, this would be pretty easy to write, and you can copy and paste this between your projects. But if you Google Gaussian processes in Python, there are 6 million different libraries that exist for it, and that's just in Python. Of course, in every other programming language has its own suite of codes that do this, and so why is that?
What does the function return? What's the output of that?
Good. Yeah. So this returns just the loss function. So for one setting of the parameters alpha and theta, it evaluates that equation right here. So it doesn't do the prediction and stuff, so yeah, there are. I'm sort of exaggerating a little bit on how simple the whole thing is, but this goes a long way to what, in fact, the other things are very simple to write as well in this framework. Yes?
I guess you should mention that once you have the factor, you can basically do the things.
That's right. Yeah. So in fact, we would normally do this in 2 steps. And there are design decisions that you may make differently if you were truly implementing this, but this goes a long way towards, I wanted to emphasize how straightforward, in fact, the core operation behind a Gaussian process is.
So GOF?
Yeah.
That's, what is that?
Good, yeah, great. So I very briefly mentioned that in our aside earlier. So GOF stands for goodness of fit. And basically, and then there's this norm. And those are these 2 terms. So this thing and this thing right here, this is the goodness of fit, and then this is, and basically these are the 2 terms that are trading off against each other. So the goodness of fit is how well are your data captured by the Gaussian process kernel that you wrote down, and then this is how specific is your kernel. So it doesn't want to just set alpha to infinity. This is the evidence integral of the model as well. Good. Okay, so like I said, in practice, a lot of the time you might, the reason why you might want to use one of these packages that exists is you want to make it easy to experiment with different covariance functions. So here I basically sort of hard coded, constructing that matrix K in here. But you want to be able to swap them in and out and try different model checking types of things. You might want to use some specialized methods for fitting for your alphas and thetas. And so there might be sort of infrastructure built around the likelihood function. Or you might want scalable methods. And so all of those things quickly get more tricky to implement compared to the one that I showed there. So here's some set of Python packages that exist to do Gaussian processes. The bottom line are all ones that I've written. I'm giving this lecture, so I'm allowed to emphasize the ones that I've written, but in fact, there are also lots of other libraries that exist. And I would say at this point, sort of the ones to choose depend a little bit on your use cases and stuff like that. But gPyTorch is a pretty good place to start. It has a lot of scalable methods. They do a lot of sort of this GPU accelerated iterative methods. They also have some approximate methods. They sort of cover all the bases. I don't find the interface very intuitive, but I'm also not a PyTorch expert. And I've seen like ridiculously good performance out of that package. And then TinyGP is my most recent code, and that's the one I'm going to show a little bit more going forward. And I'm excited about it. It doesn't like have all of the bells and whistles, but I think it's got some cool stuff in there that we'll talk about. And then if you're in a different programming language, I think there are lots of other good choices, but I don't really know the ecosystem as well as I do in Python. Yeah, here's gPyTorch. It's very cool. Yeah, let's see, what do we got here? Scalable GPs, all sorts of approximate things. And then this is TinyGP, this is mine. And one thing that I wanted to show while we're here was, so this is a slightly different version of the scaling plot that I showed earlier. And one thing that I didn't mention is, so the blue line from before is now this black line on top here. And then this blue line is the naive implementation built into JAX, so into TinyGP, which is built on top of JAX. And so the thing that you notice here is that in fact the cost for small models is much reduced. And that's one of the things that's really cool about JAX. I think there were various other people who have been singing the praises of JAX since at this workshop so far. Yeah, has there been like some like intro to JAX that has happened yet? Who here uses JAX? Great. Okay. I want to do like a little intro to JAX. It's so sweet. I'm like turning into that JAX guy who like goes around and like encourages everyone that they should use it. But you know, so okay, sure. It doesn't matter. Like I only have 10 data points here. Like who cares if it's like 2 orders of magnitude faster? But it's still cool. But the thing that's really cool is, so this dotted line here, that's my quasi-separable matrix package Celerite. And it's written, like I wrote like highly optimized C++ code that does like, you know, SIMD vectorization and also like all sorts of crazy stuff. And then I compiled it with a Python interface. And then this green line is the JAX implementation that's just written in Python. There's absolutely no C code written, and it has better performance for small models, and it scales the same for large models. And so that was pretty ridiculous. So I'm very stoked about that. Okay. I think we have like 25 more minutes. Is that right? Yep. Yeah. Good. So let's start with questions, and then I was going to do a little bit of like interactive, sort of interactive-ish live coding fun times. Any questions about all of that we? Good. Yeah.
I guess in this whole discussion, you're kind of assuming that the mean is around 0.
Good. So not necessarily. So in fact, I've written that the mean is some arbitrary function, and I'm subtracting it off everywhere. It is an important point that in the Gaussian process literature, oftentimes this will just be set to 0 without loss of generality. But I think it's useful to carry around that f, and you'll see that we also wrote it over here too, because it's important to. So you can get very bizarre results if you like try to fit a GP model to some data that's not mean centered, and like try to predict. And sometimes it'll sort of look maybe right, and then you try to extrapolate, and things go really wild. So when I fit a Gaussian process, I always fit a mean function of some sort, sometimes just a constant. We'll show that in a second. But
So that you just do least squares on like a linear regression on some basis, and that would be.
yeah, and I would normally do it simultaneously. So I would like fit for the parameters theta at the same time as I'm fitting for alpha.
That was why
Yeah. And so that's the approach that I would normally take. The other option would be to just mean normalize your data or something like that first, or do some least squares or something like that to try to remove the bulk trends. It depends on how much covariance there is, whether or not that's a good idea.
Could you do like we got both from when you get your data to when you make a prediction, like big steps?
Good. Can we do that in just a moment? Because I'm going to walk through an example in just a second. Yeah. Good. And if I don't hit on all the points, let me know. Okay. So as you're thinking, if there are any other questions, I'm going to get set up to do this. Get over here. Okay. So how do I make this go away? Okay. Pivot. That's not what I want. Where are we? Here we go. Good. Okay. Yeah. So I was going to show. So TinyGP is the one that I want to talk about because I'm so stoked about it right now. It has lots of tutorials on the documentation. The documentation lives at tinygp.readthedocs.io. And the example that I'm going to go through is something that I presented at a conference a few months ago called GPRV. So it lives at my username on GitHub, dfm/GPRV. Good. And so let's get started. So I wanted to start. So since not too many people use JAX here, and TinyGP really depends on JAX, I wanted to give like a whirlwind tour of JAX, and also just because I love it. We're going to do it on Colab. Let's see, is that okay to see? It is, let's see, yeah, there we go. Good. So JAX is just installed on Colab, and so that's nice. We don't have to install anything. And one thing that I always do is when I start a JAX project is I like to enable double precision because by default it only works at single precision, which in fact is often not very good for Gaussian process models because there can be lots of numerical stability issues. And so I always like to turn on double precision right off the bat. And the performance is generally still good. But it can be easy to forget. Good. And then the main interface that we use for JAX is the jax.numpy module. And who here uses Python normally or like often? Good. Okay. So almost everyone. And so you probably use NumPy as well. And the thing that's fun about the jax.numpy, the tradition is to import it as JNP, is that it like implements all the things that NumPy does. So it has like all the usual functions, and it kind of looks like NumPy code, which is cool. This has this weird type, but otherwise that kind of looks like what you would write in NumPy. And so I find that it's like an easy place to get started with these kinds of things. Okay, so then sort of the thing that's weird about the like programming style in JAX is that it's very functional, where like functional programming is a specific thing. It doesn't matter the details for now, but you're going to write a lot of functions, and then you pass functions to functions that return new functions. You'll see. So let's start by writing some function that takes in some argument. And let's say we take the sign of that argument. And then let's return something. Something like that. Okay, so we have a function now, and we can evaluate it just as we normally would. Okay, everything looks good. So then the first thing that happens that you do in JAX is so that our first function transformation is something called JIT. So that means just in time compiled. And so we're going to run that, and then we can call that function, and we get the same answer. Okay, cool. That isn't very exciting, but there were a few cool things that happened behind the scenes when we did that. And the first thing I'm going to do is I'm actually going to write this as a decorator. So this is the same as what I did before. So using the decorator syntax like this wraps func in jax.jit. And now this is the jitted version of this function. So we don't need that anymore. Okay, good. Okay, so then so just to show you what's happening here, I'm going to add a print statement in here. Good, so I run that, and it says hi from inside. It gives the result, right? I run that again. What happens? Okay, so you notice that it didn't say hi from inside. Can you guys see that all right? Yeah. So it didn't say hi from inside. And so what happened there? So what happened was the first time we called it, it executed the function, but actually, even more fun, let's print what it thinks x is when we're inside there. So it executed the function. I'm going to not print the output. Oh, sorry. Using this weird type. So it's a traced. X is no longer a NumPy or is no longer an array, right? And then what it did is then it built a representation of everything that happens in that function, and it builds a little C++ operation that captures the relationship between the input and the output of that function, and it hands that off to the CPU and returns the result. And you'll notice that this doesn't know about the data. It only knows about the data type and the size of the input. And so that means that when we run it again, it doesn't call any of the things inside. And if we called it again, adding 1 to it, it wouldn't. It knows how to execute. It's not just caching the result. It's caching the operation that goes from the inputs to the outputs. Now, one thing that's important is if we did that, it does have to run the function again, because I've passed in data with a new shape. And so it retraces the function every time you have a new shape. And so in the examples I was showing, the reason why the JAX version of the code was so much faster for small data is that it removes all the Python overhead. So if I wrote this in NumPy, it would be allocating tons of new arrays for every time you're performing an operation. It's allocating some new memory, copying the data over to that memory, allocating new memory, copying the data. Whereas JAX has been able to optimize all of those things out because it knows like exactly what the relationship between all of the data is going forward. And so good. So that's the gist of it. So okay, the gist of it. Good. Okay, so that's cool. It's not, so if you're familiar with like Numba or something like that, the JIT is very different from that, even though it has the same name, and the performance constraints will be different, but it can make your code quite fast if you have a lot of small memory allocations and things like that. So the next thing that I wanted to talk about was VMAP. We're a bit. We're going to skip VMAP, and we're going to talk about instead. So the other thing that JAX has besides this JIT is automatic differentiation, which I think we have talked about here. And so what we can do is wrap our function in this value in grad function, and that now gives us some function which we can call, and this will throw an error. Only defined for scalar output functions. So what can we do about that? So there are a few options. So and the reason for that is that generally you want to be taking derivatives with respect to like a loss function or something like that. So you're normally taking derivatives just with respect to a single output. So we could just do something like that, and that'll work. So that gives us the value of the function and then the derivative of that function with respect to x evaluated at that point. So that's cool. And we could also use the VMAP function, which I didn't show you, to get the other thing, the thing that we want, which is the function value and its derivative everywhere. And so we plot that. It was a little bit, whatever. You get the picture. I'll make it a little bit bigger. There we go. So now we have the function value and its derivative, and we never had to write down what the derivative was because of automatic differentiation. Yeah. Oh yeah, of course. Sorry. Yeah. And what the VMAP function does, I'm not going to show it, but it converts a scalar function into, it sort of does the broadcasting itself, which seems maybe like a little trivial, but because NumPy does a lot of automatic broadcasting too. But it can end up being really, really nice to have this kind of detailed control over the broadcasting. And I'll share the notebook afterwards as well. So then the last thing I wanted to show, because it's like hugely undervalued, is pie trees. So pie tree. And so let's say we want to parameterize our function here, and so now params is going to be a dictionary. Okay, good. So params is a dictionary with a the let's see, say something like that. Okay, and then this is going to be like really unimpressive, but we'll get there, I promise. Okay, so we called that, we passed in a dictionary, it did what we expect, right? So NumPy knows how to do all of those things. But what if we then take the this, oh, we need it to be a scalar output. So let's add a sum here. And so what happens if we take the value in grad and run autodiff on this function? What it produces is the derivative, the gradient here has the same structure as our parameters. So we have the derivative with respect to A in a dictionary. And it also, this supports all of the other kinds of things without computational overhead. And so this ends up coming in really handy. And so it's worth knowing about. Anyone impressed? I'm so impressed. I'm so stoked. It's very cool. It's like the most undervalued feature of JAX. Good, okay. It's fine. It's fine.
Does it matter that the, like if you pass a dict versus like a tuple, does it affect the performance at all?
No, so that's the thing that, so I mean, there's maybe some minor overhead in the tracing, but the thing that's cool is that in the background, before it executes your function, it flattens everything. And so it's just operating on arrays passed around. So in fact, the performance is very good, even with these structured data types, which is very wild. Yeah.
Does it just receive any iterable?
Say again?
Does it just receive any iterable?
So yeah, it can deal with lots of different things. So tuples, dictionaries, named tuples, and then you can register your own data types as well. So it can handle all sorts of different things. So like I'm working on a project right now to like add units to JAX, and I registered a custom unit type that then knows how to operate within this framework. Okay, so now we're finally going to get to Gaussian processes. And so I'm just going to install two packages here, my TinyGP package, and then this JAX opt package, which can come in handy. And I've generated some simulated data here that has some periodic covariance where the period is in fact varying as a function of time.
The notebook on, like, is the notebook online where we can?
Yeah, so
open
it's
the collab?
yeah. Oh, the collab, no. Can I like share it, or maybe that's too
Yeah,
complicated.
you can share it and send
I'll definitely send it around afterwards, and then there's a version of it in this GitHub repository as well, with sort of all executed when I was practicing.
Yeah, I think so. I think you can open like an arbitrary notebook in Colab if you do /GitHub.
Right. Yeah, but this one doesn't have anything in it because I'm live coding.
Oh, sorry. I thought it was like filled. Okay.
No, I just entered the data simulation process because I didn't want to have to live code that. Okay, so we have this simulated data, and I want to fit a Gaussian process model to this. And so, oh yeah, we have to remember to do this, and then from TinyGP for kernels and Gaussian. Good. Okay, so those are our imports. And the way that you build a covariance function in TinyGP is under this kernels namespace, we have a bunch of kernels. So say the matern 3.2 kernel, this is our L parameters, our length scale. And then if we want to put in amplitude, we can just do something like that. So we multiply that by a scalar, and that gives us a new kernel. That's the product of two kernels. And then we can multiply that, say, by another one. And so this is what I meant when I said before that generally you want to like choose a basis of kernels and then combine them by adding and multiplying them like this. Let's see. So there's something like that. So here, this is our initial kernel, okay? And then we create a Gaussian process object with that kernel, and we have our x's and our I simulated error bars too. So we're going to put those in, and then we can compute the come on, give me some love. There we go. Good. And this is going to build that kernel, populate the covariance matrix, and then solve our favorite equation right here. And so this is the thing that we want to maximize in order to fit for the parameters of our kernel. And this is a way of computing it using JAX throughout. So in the background, this is calling out to JAX. And before I show actually fitting, let's look at this prediction step, right? So the way that you predict with TinyGP is you call the condition function. So you're conditioning on data, and we're going to give it some new x's. So I defined up here my x's were my observed x times, and then our x grid was some finely spaced grid across that whole baseline. And so I run that, and then this is a named tuple that comes back with one of the objects is the conditional Gaussian process, right? So the conditional is also a Gaussian process, and we can do various things with that. So we're going to plot what our sort of initial predictions are here. I'm going to start by plotting the data, and then our Gaussian process object has a mean and a variance, which we want. I'm going to take the square root of that. And that's. Oh, that was bad. Did I? That looks worse than it should. Oh, that's why. There we go. Good. So that's our mean prediction. So that's mu that I've written there. And then a common way of plotting the predictive variance is something like the following. Something like this. So that's like our 1 sigma confidence for our prediction here, and you can see it's sort of a little wobbly. It's not the best, but you know it's not a terrible starting point. And you may do like the like 2 sigma contours underneath or something. Do that. But yeah. So that's like how you would plot that prediction. Okay. So in our remaining 2 minutes, I'm going to show you how to fit this. Okay. So the way that the like workflow for this is generally we would write a function to build our GP object, which you'll see why in just a second. And we're now going to have some parameters. So, and it's important, we often use the log, we'll often fit in the log of our parameters when they need to be positive. So like our amplitude needs to be positive, and so I'm going to fit in the log amplitude and then exponentiate it. Similarly with our length scale here. Say again? Oh yeah, so I want amplitude to have units of y, not y squared, and so the covariance has units of y squared, and so this is equivalent to that. Sorry. Cool. Okay, and then I said I would fit for the mean too. So we're going to fit for a mean value as well. Okay, so this is a function to build our GP, and then we're going to define the loss function, which is pretty straightforward. It's build our GP with the parameters, and then we're going to compute its log probability at y, and then we're taking the minus sign so that we have the negative log probability because everyone likes to minimize rather than maximize. Our initial parameter set is going to be something like this. Okay, and so then if we do that, it computes the loss. Cool. And we can do it, we can JIT it because it's all jacks in the back end. And then in order to fit for the best fit parameters, I'm sorry, we're going a little over, I swear I'm almost done. It's just the worst when people do this.
Good. When you wrote the mean like that, is that like a constant function?
That's right. Yeah. So so alternatively we could make this a function that takes an x as input, but that was a little bit too much for today. Okay, so it's as simple as this. So we choose some initial parameters, and then this is using scipy.optimize.minimize in the background to just minimize. And the reason why JAX-opt is nice is because it handles all of these pi trees properly. So it takes into account the fact that we're using these structured inputs. It's going a little slowly. It's probably a bad sign. And it comes back with some parameters. So it thinks those are the best fit parameters at the end of the day. And so let's make our plot again. So we need to, and we're going to build our GP using that function that we wrote above with the best fit parameters. And then we're going to condition on y. And then let's see if it's any better. Fingers crossed. Oh, it's horrible. What have I done? Oh, that's why. I shouldn't have made the X grid and the data the same size. I keep on just plotting it on the wrong X coordinates. There we go. That's better. Okay, so and so now we have we've found the maximum likelihood setting for those parameters, and we can make predictions in the section of missing data and in the future and in the past. And this is the point where you might want to start doing some like model checking, cross-validation types of things to make better decisions about your choice of covariance function. But yeah, that's sort of the workflow for as far as it goes for how you would work with something like this.
Okay. Thanks, Dan.
Okay, so today we are very glad to have Kyung Cho, who is, I don't think he needs much of an introduction, but he is one of the world leading experts in NLPs. He revolutionized RNNs, he invented GRUs, and he's currently in the process of revolutionizing protein design. No joke, it's true. And he was also my mentor during my later postdoc years. So I owe a lot to Kyung. Please.
Oh, thank you. Thanks for the invite and welcome to Flatiron Institute. It's glad to have you, see you all. And then I looked at all the applications of you, and then you're all amazing. And I forgot to actually send Sebastian what kind of lecture I was going to give. And yesterday I checked Twitter, and then Miles kind of decided that I was going to talk about natural language processing, whatever that means. It's a bit too broad. So I thought, okay, we're going to choose what we're going to talk about today for the next hour or so, democratically. Okay, so I have 4 talks that I can just give. Actually, there are a couple more, but let's say 4 of them. The first one is on protein design. As Sebastian says, I don't know much about proteins themselves, but it turned out that many of the advances that we have built in machine learning and adjacent areas such as natural language processing, machine translation, and whatnot, turned out to be extremely impactful in protein design and thereby more generally the drug discovery. So that's the first possible topic. That's going to be the intersection between machine learning and biology. The second potential topic is machine translation. So that's the thing that I've worked on for let's say about almost 10 years now. Okay, so the time is fine. 10 years now, and then I can give you some, let's say, background about what kind of, let's say, techniques are used in machine translation these days, and then what are the things that are not really working well. Because often when we hear about all this news about what was the word? Sentimental? No, sentient. Let's say AI or whatnot. They all talk about the large-scale language models, and it almost feels like everything has been solved, but it turned out that is not the case. So that's going to the second topic, and then that's going to have a bit of a machine learning and a bit of a linguistics angle, or more specifically computational linguistics angle. And the third one is going to be data augmentation for natural language processing. Now, this one is slightly incorrect in the sense that all the techniques that I can talk about are on the data augmentation, but there is a learned or the trainable data augmentation. But I'm going to use the natural language processing as the target domain, where we can actually show that the machine learning algorithms can be used for us to come up with a novel data augmentation process without any manual, let's say, design. And then the final one is more on the just the machine learning side, as in that's more on the generative multitask learning. But the fourth one is only about, let's say, 25-minute long talk. I can, make it longer, but I think it's going to be a bit short. But of course, I can mix it with another thing. So let's try to see who wants to hear about what. Who wants to hear about the protein design? Please raise your hand. All right, I count. Okay. All right, 7. Who wants to hear about machine translation? Okay. Oh, well.
Can we vote twice or only once?
Oh, that's a good question. Okay, let's restart. So you can actually raise your hand up to twice. Okay.
I will.
Oh yeah, okay. So we need a counting here. Okay, so let's start from the top. Okay, first talk is on protein design. Please raise your hand if you want to hear about it. 8, okay. All right, and machine translation. 5, okay. Data augmentation. 5, 6, okay. Generative multitask learning. Oh, okay, 9. So the winner is generative multitask learning. We'll start with that one, and we'll come back. If the time permits, I think the final one is actually shortest one. If time permits, we'll go to the next one. Okay, in the list.
I think this is the first time I've ever attended a democratic talk.
Yeah. Okay, there you go. Multitask learning. All right, let's see. So this is the talk that I prepared just last week, actually a few days ago, as in like the Wednesday. It's less than a week old, but this is based on a work that I have done together with my PhD student Tara Makino and Christoph Garris, who used to be my postdoc, but is now a professor at the radiology department in the NYU Langone. And we decided to look at the multitask learning because multitask learning is one of those things that fascinates most of the ML practitioners because it has amazing promise. But we're going to talk about what multitask learning is first, and then trying to get to what we mean by generative multitask learning. So let's see if it works. Okay, of course not. All right, so in order to get to the multitask learning, you probably have learned already about the supervised learning, but let's just go over what we mean by supervised learning first. And supervised learning is indeed, the only, let's say, machine learning technique that has been used in practice, and we know very well of all those theoretical properties, and can have and already have made a lot of impacts on the various domains beyond computer science. And in conventional supervised learning, our goal is to build a system, f of theta, that's going to take as input some input variable x, and then tries to predict what kind of category the input belongs to. And how we are going to learn this multitask learner, sorry about that, the supervised learner, is to use a data. So we're going to have some data set that has been collected either manually, experimentally, or in some kind of synthetic process, let's say simulation. And then we use the data to induce this supervised learner f of theta. And in conventional supervised learning, perhaps unsurprisingly, as we make this supervised learner more and more powerful, it all comes down to regularization. So a lot of people, like they feel like, oh, we need to come up with a better supervised learner in this way and that way and that way. But it's actually all pretty much a moot point unless we can regularize learning strongly so that that system after training is going to generalize to unseen examples. And what we mean by regularization is to limit the representation capacity of this supervised learner f of theta. And how we build this kind of supervised learner is actually relatively straightforward. So what I mean by the straightforward, there are actually a few criteria that we just have to keep in our mind. One is that we need to be able to solve the optimization problem well enough. And then two is that we need to give enough, let's say, nonlinear computation, or the number of the layers of the nonlinear computation, so that it can represent a very complex functions. And then that actually leads to all those, let's say, neural nets that you have already seen, used, or learned about, such as a residual network. Residual network consists of the many, many nonlinear layers, but in order to facilitate optimization, we had to invent and introduce those shortcut connections. And in the case of the transformers, what we wanted to do was exactly the same thing. A lot of nonlinear layers. We use a residual connection in order to introduce all the shortcut connections. But then we wanted to make a supervised learner to work with any sized input. So the input without any specific size. So we had to introduce a self-attention there, and on and on. And then those are very few critical blocks that you need to know in order to build any kind of supervised learner that is able to solve almost any problem that you want. There are some limitations there. However, in that case, what we need to focus on is regularization. So until about 2016 or 17, indeed, we wanted to introduce all those as a critical building blocks, but nowadays it's all about regularization. So we're back to, let's say, this square one, yeah, back to square. Anyway, so there was a conventional supervised learning where we want to solve just one problem. And then when I say one problem or the one task, that actually corresponds to one type of the target. So why? Now in multitask learning, we want to actually build a system to solve the main task y, while making it also solve the auxiliary task y prime. And when we try to get that f of theta there, what we try to use is not only the main task data set D that consists of the x and y pairs, but also the D prime where we have the x and y prime pairs as well. So you can imagine that instead of training a model, let's say machine translation system to translate from English to French only, we're going to train this machine translation system also to translate English into, for instance, Korean. And then while we want to do that, there are many different reasons. Perhaps we want to solve both of these problems equally well. Or better yet, perhaps this auxiliary task y prime can work as regularization. So by making our model f of theta solve both y and y prime, we are constraining what this f of theta can solve for y. So this is one way to introduce the regularization, and it's been quite successful. In fact, if you have ever used a Google Translate or any kind of machine translation systems that are off the shelf or they're commercially available, most of those systems are nowadays so-called multilingual systems. When you try to, let's say, translate English to French, and then you use the same system to translate from English to German, in the background, there's a one neural network that does that. And then that is one of the representative and most successful example of the multitask learning. However, unfortunate thing is that that is probably the only successful multitask learner that we know, because most of the other cases, multitask learning doesn't seem to help. It doesn't hurt, but it doesn't seem to help. Now, why does it not help? perhaps we can start thinking about some of the extreme cases, because it's always a good idea to think about the extreme cases and then try to rule out whether those extreme cases are happening or not. And then from there on, we can try to figure out why this kind of, let's say, paradigm should work and should not work. So in one extreme case, I said the extreme case because this is like indeed the most extreme, but a extreme case here is that the multitask learning simply reduces to single task learning. So we talked about how powerful the supervised learner is becoming or has become. And then when we're trying to train this supervised learner to solve these two tasks, y and y prime, what can easily happen is that the supervised learner is going to simply split itself into two partitions. The first partition tries to solve the main task y, and then the rest of the partition, rest of them is going to try to solve the problem, the auxiliary task y prime. And what that means is that it's as if we actually did not have the auxiliary task at all. And then that's exactly the opposite of what we wanted to happen, right? So what we wanted was that the y prime is going to work, or trying to solve y prime, it was going to work as a regularizer to solving y. And surprisingly, this happens very, very easily. You can actually make a synthetic example of the multitask learning, and then you just plug in, let's say, some ResNet or the fully connected network that you know how to train. Then you train it well enough, then what happens is you actually can see this happening. Now, how do I know that this happens? Is that I can plug in another linear classifier in the middle after training is done, and then try to ask this linear classifier whether which dimension actually is trying to solve the problem of the main task or the auxiliary task. And then you can actually decode it out, and then you see that there is a clear separation between within the space into two partitions that corresponds to the main and the auxiliary tasks. So what we actually hope and what we expect to see is rather this. Is that because we're going to train this supervised learner to solve both the main and the auxiliary tasks, we want this supervised learner to first extract a very useful feature that is useful for both the main and auxiliary task. And then at some point, it's going to branch out into the main task branch and then the auxiliary task branch. And then thereby, solving the main task benefits from solving the auxiliary task via this shared feature extraction stage. And then this is precisely what we want, because this is going to allow us to learn a better representation that, let's call it G of X. This is really idealized picture. And then that's what everyone thinks is supposed to happen. And truly so, if you look up, let's say, multitask learning or the papers that claim to use multitask learning for solving some of the problems, this is exactly like the half of their paper, trying to justify or motivate why they want to do the multitask learning. And eventually what they say is that because of this, they're going to get a better representation coming out of the different tasks. Thereby, this learner can actually learn to solve the main task better. But no one actually tells us, exactly what actually drives this kind of this learner to get this better representation, rather than the extreme case that we just talked about, that is just splitting the space into two partitions. In fact, there is a seminal PhD dissertation by Rich Caruana that's from 1998, and the dissertation was titled Multitask Learning. And that is like really the pinnacle of how multitask learning can be done with artificial neural networks. It's a really nice dissertation. I recommend you to take a look at probably the first chapter or so, not the entire thing, because at some point, Rich also realizes that he doesn't know why multitask learning works. So at the end of near the end of the section, chapter 2, if I recall correctly, he actually talks about some of the conjectures that he has about why multitask learning should help, and then why we would benefit from having multiple tasks rather than trying to solve the main task as close as possible. Question, yes?
So there's no crosstalk between f and f prime, and there's no like shared weights between them, right?
There could be. So yeah, when I actually partition it, it's actually not about the parameters themselves, but more like from a functional perspective. So they might actually share the weights, but then you can imagine that if you look at the actual activations that are being used, even if the weights are shared, they might just be completely separated, right? So some, let's say, dimensions are going to be used only for let's say predicting the y prime, there's some other dimensions, or they don't have to be aligned perfectly with the dimensions, right? So the axis and so on. So yes and no, yes and no. Yes. So what Rich Caruana suspected were, let's say, potentially three things, although all of them turned out to be exactly the same thing. The first suspicion he had was that there is some kind of statistical data amplification effect. Because now we have the data set, there are two data sets instead of just one data set that was about the main task. Perhaps simply having more data imposes more constraints on the parameters, effectively narrowing down the hypothesis space over which learning happens, and then that magically constrains the hypothesis space with into the subspace that contains a better generalizing, let's say, solutions. That feels a bit too magical, so let's look at the second one. Attribute selection. What he meant by attribute selection is that if we have only a small amount of data to solve a problem, then there's always ambiguity in which features are important. Now let's imagine that you're solving a linear regression, very simple model, but it turned out that linear regression is one of the most difficult models to analyze if the input features are collinear or statistically dependent on each other. Because every time you train it, it's very possible that you get the same quality linear regressor. And then it depends on whether this linear regressor decides to look at a particular feature or another particular set of features that are collinear with the original feature. And then the kind of ambiguity makes it really difficult to solve a problem well that's going to generalize. So the having more data or the having this auxiliary task, which shares the important features with the main task, perhaps allows the supervised learner to select the important, correctly important features better. Okay, maybe not, but then what does it mean for the auxiliary task to be related with the main task? That's also not really well defined. Third suspicion he had was what he referred to as a eavesdropping. I have absolutely no idea. I read his dissertation from the beginning to the end. I still don't understand what that means. So let's pass. And then the representation bias is exactly what this figure shows. Is that somewhere in the middle, this learner is going to learn some kind of a shared representation that has to be beneficial for solving both of these tasks. And then the bias is the beneficial bias. Okay, too magical still, right? So why would that be a beneficial bias? And all these suspicions or the conjectures can be summarized largely as you're having more data by trying to solve this yet another task. And it's very difficult to formalize and evaluate whether any of these factors happens, unfortunately, in this kind of current setup. So one way to do machine learning research is to try to figure out the setup in which machine learning algorithms or the paradigms that we often use are provably helpful. Just knowing when some of the algorithms are going to be provably helpful is very useful, right? So then the next time we run into a setup or we run into a situation where we need to solve a problem, if I knew that that problem actually does follow roughly the setup that I know certain paradigm is going to probably work, then I'm going to just use this paradigm. So what we decided to do is, okay, let's try to answer these two questions. One, can we come up with a setting under which multitask learning has to work? So if we do the multitask learning in particular setup, it will work. So let's try to come up with that. And if such a setting exists and we are able to find it, then what is the right way to do multitask learning? Multitask learning itself is a bit vague, right? So what does it mean to do multitask learning? There are many different ways to approach it, but perhaps we could find the setting under which multitask learning has to work, and under that setting, we may be able to come up with the right way to do multitask learning. So to do that, we're going to actually take a few steps, going from the very basic, let's say, discriminative single task learning, all the way to what we refer to as generative multitask learning with a target causing compound. We'll go through it one step at a time in order to figure out what is the precise setting under which the multitask learning has to happen. So I presume most of you are familiar with not familiar because I'm not familiar with it, but roughly, let's say, knowledgeable of the probabilistic graphical models. Yes. Okay. I'll take that as yes. All right. No answer is yes by default. That's the most important principle in machine learning, right? So in particular in reinforcement learning, optimism in the face of uncertainty. I'm very uncertain about what you know, but I'm going to thereby assume that you know everything already. So let's start with the discriminative single task learning, which is the most basic form of supervisor. So we have two random variables, x, let's see, does it work? Yeah, x and y. And then x is the input, y is the target or the class to which input belongs. And then both of these are random variables. What that means is that we have some distribution over x, and then we have a conditional distribution y given x. And what we're trying to do is to, by the process of learning, we're trying to ensure that we estimate this conditional distribution over the class or the output given the input. And how we do learning is often just simply following the maximum likelihood. That is, we're going to look at all the data points in our data set, then trying to ensure that our model, characterized by theta, is going to assign as high a low probability as possible to the correctly paired output given the input. And once training is done, we're going to simply use this classifier that has been trained in order to figure out what is the y that has the highest low probability assigned by our model. So very straightforward, but let's keep this in our mind because the next step is going to flip the arrow. So in this generative single task learning, we start with the category y or the output y, and then given the category, we define the conditional distribution over the observation. So all we did was to flip this direction of the arrow. And then this is what we often refer to as a base classifier, as opposed to logistic regression. So the previous one is going to be, we often call it as a logistic regression. And this one, we often call it as a base classifier, or with certain type of the assumptions, we may call it a naive base classifiers as well. But only difference is that are we going to model the conditional distribution over y given x, or are we going to model the conditional distribution over x given y? And learning is pretty straightforward, except that now we are actually trying to get the relationship going from y to x. And then at the same time, we're going to now take into account the low probability over y, that is a marginal distribution over classification. And then inference time, the same thing, because we have already trained the model, we're trying to find the category y that's going to maximize the score that is assigned to by our model. Strictly saying, it's exactly same as a discriminative single task learning, but we have a better control over the target distribution P of y. So that's a very subtle difference. That is that in the inference time, if we go back here we just simply rely on whatever our model tells us, right? So given this x, what should be the distribution over y? But in the case of the generative single task learner, what we see is that in the inference time, we need to think about, theta is actually missing here. We need to think about two things. One is what our model tells us about how likely the observation is given one of the potential output, plus how likely that output itself is under the prior distribution. And then what it tells us is that if we want, once training is done, we can actually replace this marginal distribution as well. And that actually tells us a lot about what we should do in terms of the target distribution. Since it's a lecture in the summer school, so is everything clear so far? The difference between the discriminative and generative classifiers? Yes.
So this is like maximum likelihood, kind of?
Oh, everything is maximum likelihood so far. Yes. Yes. Everything is maximum likelihood so far.
Okay.
Yep.
Is there any difference in terms of how you compute like the two quantity probabilities, like the class given the the x or the opposite?
Right. So essentially what is the actual difference between these two, right? So to be strict, as you know about the base rule, in fact, you can always flip the arrow. You can always flip the arrow, right? So what that means is that the distribution-wise, if you had, let's say, this graph and this graph, they don't really differ much, right? As long as you choose the conditional distributions and prior distributions in a way that are compatible with each other. But what is different, and then this is the difference between statistics and machine learning. Well, actually, probability and machine learning is that what is different is what is the particular distribution that we're going to model with our machine learning algorithms. And then that does make a difference because one direction may be easier than the other direction to model based on a finite amount of data. So that's the reason why often in practice, one of these approaches tends to work better than the other in terms of generalization, given a finite amount of data that is available to both settings. But strictly saying, we can always flip the arrow, however we want. All right. I know, so basic, but this is what happens every time. You gotta come back to basic and so on. Yes. So let's see. And then now we can think of the multitask learning from the same framework, and we're going to start from the discriminative multitask learning. So again, the arrows are going up, starting from the input observation, and then given that observation, we now have a distribution over y and y prime. And this discriminative multitask learning, what we assume here by drawing a graph like this, we assume that the y and y prime, so the main and the auxiliary tasks, are conditionally independent of each other. That is given this x, the observation. And if you try to write the maximum likelihood learning criterion, we're going to go through all the triplets in the data set we have, x, y, and y prime. And for each one of these, we're going to try to ensure that our model, so p theta and p theta prime, I just separated out to ensure that, okay, they look like two different things, to maximize the log probability assigned to the correct y and then correct y prime. Then we simply train a model to do so. The interesting thing about this discriminative multitask learning and what it shows us is that the after training is done. So during training, we need to look at both y and y prime. But then once training is done in the test time, we actually don't care about the y prime at all. Because this particular factorization actually tells us that the given x, so in the test time, we're given x, right? Given x, y and y prime are independent of each other. So while we actually care about y prime, we don't care about it. We only care about y. Yes?
I would think that multitask learning will help us in the case where they are not independent, precisely, not in this case.
Right. Exactly, right? So this case doesn't look like it's going to be helpful. But then if you think about it, let's just go back to what the usual, let's say, practice of training a multitask learner is. This is the usual practice of building a multitask learner. There's the input x that goes into our neural network. And then this neural net is going to compute, let's say, categorical distribution for y, and then yet another categorical distribution for y prime simultaneously. That is, in fact, precisely how this discriminative multitask learner is factorized. So yes, it doesn't look, now that you look at this, it doesn't look like having y prime should necessarily help y. However, if we think, if we didn't look at it from this angle, and then if we only thought about the multitask learning from this angle, we can get a kind of false sense that the multitask learning would always help because of this nice shared representation that should be useful or beneficial for solving both of these tasks. So yes, great point in a sense that there is the point of this side. So this auxiliary task y prime is used during training, but somehow is thrown away in the test time because of this particular factorization that has been chosen. And then this factorization, this conditional independence makes it really difficult to see how multitask learning helps. We have to rely on a bit of a magic of, let's say, stochastic gradient descent and neural network. But the one thing I can tell you, and then you're all scientists, so you should know better, is that it's not a good idea to rely on magic to prove a point, right? Not good. So then now let's flip the arrows again, just like what we did with the discriminative and the generative single task learning. So in the case of the generative multitask learning, we're going to say that the given y, the main task, let's say output, and the y prime, the auxiliary task output, given these two, we are going to define a conditional distribution over the observation x or the input x. And this is generative multitask learning in the sense that our observation is generated from these multiple tasks, and then we're trying to use a neural net to model this generation path. And learning, in doing learning is again going to be maximum likelihood learning. We're going to go through all the triplets in the data set, and we're trying to maximize the loop probability assigned to the correct observation given the correct y and y prime pair. And then we have the log p of y, log p of y prime, but these two are just a marginal, so we can use whatever the techniques separate in order to get it. Now, interesting thing is, once learning is done, in this particular instance of the generative learning, in generative learning, we actually do need to find the y and y prime, the combination of y and y prime that's going to maximize the log probability assigned to this observation x, given those the combination. So that's slightly different from the discriminative multitask learning, but a major difference is that in the test time, in discriminative multitask learning, we threw away y prime. But in this generative multitask learning, we cannot throw away y prime anymore in the test time, because the objective function that we try to maximize during the inference or the test time is a function of both y and y prime. So it turned out, in particular, in this case of the multitask learning, the direction of the arrow actually does matter. If the direction was flipped, so going from x to y and y prime, in the test time, we can ignore y prime, but in the case of the generative model where the arrows actually point from the upward down into the x, we now need to take into account both y and y prime. Okay, so it looks like finally we found a setup where both main and auxiliary tasks actually matter during both training and test time. Took us long to get here, but yeah, we got here, all right. But then of course we have a follow-up question. So in this setup, y and y prime, both of them matter. But does that mean that we have to do multitask learning? Right. What if we simply say that we're going to marginalize out this y prime and then look at only the y and x here? And how do we do that? Is by simply dropping y prime from data, because the data that we look at x and y without ignoring y prime is still a valid set of samples drawn from the joint distribution between x and y after marginalizing y prime. So it's all the same thing.
Yeah, sorry, when you say do multitask learning here, you mean that it's helpful to the model that we have.
Yes. Well, so yeah. Okay. Let's be a bit more specific. So let's say your idea, I want to ignore y prime. Yeah. Okay, in this model, and then that's going to be same as trying to marginalize out y prime. Look at the joint distribution between x and y. And of course, I can rewrite that into the p of y, x given y, and then the p of y. And then I can actually maximize the likelihood of p of, let's say, x given y using the data set by simply ignoring y prime. That's actually exact. Because the set of samples that I use from the training data set are the samples drawn from this joint distribution between y, y prime, and x. So if I simply ignore, let's say, y prime from this data set, that's a valid set of samples drawn from the joint distribution between y and x after marginalizing y prime. So I could just simply say that, this looks a bit too complicated. I'm going to reduce it into generative single task learning and then ignore half of the data points or the labels. And still, there is going to be a valid maximum likelihood estimator for learning and also for inference as well, test as well. So in other words, yes, it looks like the generative multitask learning is where having both of these tasks matter in both training and test time. But that doesn't necessarily mean that we have to do multitask learning, because we can simply ignore the y prime. Right? So we don't have any guarantee that using y prime should be better than throwing it away. which is kind of weird thing to say, but that's true, right? So yes, it feels like, we always feel like, more data, the better. But that's not necessarily true. In fact, it's almost always false. The data has to be collected with the purpose that is aligned well with how we solve the problem. Otherwise, the data is pretty meaningless. And here the question is, data somehow has been collected already. Now, but what is the setting in which that aligns better with how the data was collected to make most out of it? And then it doesn't look like the generative multitask learning itself is, or we cannot tell exactly. So then let's try to introduce another random variable here to make the setting even more specific, but under which the multitask learning should be helpful. In some sense, right? I'm not saying that in what sense, but we're going to talk about it. So let's say instead of y prime, and then x with the arrows going from y to x and arrow going from the y prime to x, which was a generative multitask learner, we're going to say that the y and y prime were not sampled from the prior distributions that are factorized between these two, but that they actually there was another variable z that we don't observe, and that z gave rise to y and y prime. So let's just go back and see this comparison. So this was a generative multitask learner. So a priori, y and y prime are independent of each other. And then we draw samples from these two prior distributions. And then given y and y prime, now we can compute the conditional distribution over x. And then that is the generative distribution. But on the other hand, we can even make it narrower down by saying that there exists a unobserved target causing compounder z that gives rise to y and y prime. So we're going to sample z from some unknown prior distribution. And then given that, we have the conditional distribution over y and y prime. This conditional distribution is factorized, and then we sample y and y prime from this conditional distribution. And then given those y and y prime, we have the distribution over x, the observation. So it's a bit mouthful, but we're going to call this setting a generative multitask learning with a target causing compounder where the target causing compounder is C. And one major assumption here is that we don't know what the target causing compounder is, that is unobserved. If you observe it, it's very easy. If you observe everything, everything is always easy, but we say that we don't observe. And what actually this says is pretty simple. Because we have C that gives rise to y and y prime, and we don't observe Z, we have to think of marginalizing out this C. And what that means is that now we cannot write the probability over y and y prime, this joint marginal target, so joint marginal distribution over targets. So we have the both targets, main and the auxiliary targets, into the product of the marginal distribution over y and the marginal distribution over y prime. So they are not independent a priori anymore. And in that case, what is interesting, we're going to look at what is interesting. One thing that changes is that previously we had the sum of the log py plus log and the log py prime, but we don't have that anymore. We always need to now look at the joint distribution between these two tasks. And then this actually connects to your point, is that now y and y prime are not independent of each other, even a priori. So even if we think about the prior distribution, they are not independent of each other. And then because it's a generative setup, even if we observe x, due to the so-called explaining away effect, the y and y prime are not independent of each other. Okay, so good. So we continue to take into account both y and y prime, and we now have to take into account the statistical relationship between y and y prime as well. And then that actually gets us to a place where we can now talk about why multitask learning is a good idea in this setting. And to think about that, we need to start thinking about a bit of a concept from the causal inference. Yes.
Yeah, so on the previous slide, it's So in terms of like a base classifier, now you're modeling P of the joint given X, right?
Yep.
So don't you need to do some marginalization or something then? Or because you're actually interested in one task, right? Or in both?
Oh, we're interested in one task, yes.
Yes.
Yes. So you can marginalize this out, but I'm going to actually tell you exactly why we shouldn't marginalize this out in this particular cell, in fact. So let's see, let's go back just to go through it once more. So in this generative multitask learning, if we want to do the inference, then we have to look at the y and y prime together because our parameterization of x given y and y prime, this generative distribution, was done with a single monolithic, let's say, neural networks. So we can't really decompose this into two terms. Okay, so we need to look at both of them. But that doesn't really mean that this is better than simply ignoring y prime, that is equivalent to marginalizing that out, and then doing the usual generative single task learning. Right.
I see.
Only thing that there is that we're going to use potentially more data, just because we have y prime, and then that often works as imposing a extra set of constraints on the parameters or the hypothesis space. So that may be helpful, but that's the part that we were not satisfied with, is that well, how is it helpful? Why is it helpful? So what we do now is to introduce this Z, the target causing confounder, now that the P of y and y prime are connected with each other. In fact, the marginalization itself becomes extremely tricky. Although we can do it, but I'm going to show you why that is not really the beneficial thing to do. All right, before we continue with this, any other further questions? It's just a very simple, if you look back later on, simple thought exercise of what are the different ways in which we can build this kind of supervised or the unsupervised models, and then what are the implications or the consequences you get by making different sets of assumptions. And we're going to look at a particular consequence. Again, the very straightforward notion, but that is motivated from some of the concepts in causal mechanics. So if there's isn't any further question, let's continue. So we have this graphical model where we start with a Z, the unobserved target causing confounder, that gives rise to both y and y prime, so main and auxiliary tasks. And then given the main and auxiliary task labels, now we give rise to X, the actual observation we give. Now let's say we decided to ignore this y prime. Just like what we talked about, that is that we're going to say that, well, who cares? We're going to just look at the joint distribution between x and y after marginalizing out y prime as well as z. If we simply look at the data set, original data set D, and if the assumption of this target causing confound, generative multitask learning with the target causing confounder was correct, and then that's how we collected the data, then simply look at the x and y corresponds to looking at all the data points from after marginalizing z and y prime already. But when you do that, that is we don't observe both z and y, so we don't observe either of them. What happens is that there exists now two paths via which the choice of y affects x. So choice of the y affects x via this direct path that we have actually drawn. And there is the other path that is going via z and y prime. And then this is what Julia Kerr refers to as often a backdoor path. So statistically saying, as I said earlier, these arrows don't matter because we have the base rule that tells us that we can always flip the arrows however we want. And then we can always marginalize things out so that we can remove all those random variables. But if we believe that this is a causal data generating graph, so this is a graph that tells us about how causally data was collected, then now the arrows actually do matter quite a bit. And then we can now look at what are the dependencies there is between x and y. And then based on what kind of things are observed, we know whether the dependency has disappeared or not. But along the line, if we don't observe neither z nor y prime, then there are two ways in which y, the choice of the y, affects what kind of values are likely for x. One is via the direct, let's say, the path, and then the other one is via the backdoor path that is open due to our kind of, let's say, choice to ignore Z as well as both Y prime. And then this actually prevents us from correctly identifying Y to Z, X as a relationship. Now, this is not going to be an issue if you think only about the prediction. But if it's going to be an issue, if you are actually concerned about how Y truly affects X. But I'll get to you what I mean by that shortly. But this is the backdoor path that opens up when we do a single task learning under this setup. However, if we actually do multitask learning by looking at both Y and Y prime, both the main and the auxiliary task, this backdoor path that was open going from the Y to Z to Y prime to X is closed by the deseparation principle. And by doing so, assuming that everything is perfect beyond that, we can now correctly identify the causal influence of Y and Y prime on X. So we now know what the choice of the Y, or what kind of this influence the choice of Y has on X directly. And this leads to what we call a robust classifier, or the invariant classifier, where it's the invariance to the change in the value of this Z itself. That is the unknown confounder, unknown target causing confounder. What does that mean? Even if the Z value changes, or the distribution over this Z changes between the training time and test time, it really doesn't matter, because we actually block this backdoor path that's going to be affected by the choice of the distribution over Z. So in this particular case, if we use the paradigm of multitask learning instead of the single task learning, we can provably build a more robust, or the invariant predictor of X given Y and Y prime. So this is a one setup where we know that we're going to benefit from multitask learning as opposed to single task learning. If we just ignore Y prime in this case, it's definitely not going to be a robust solution. I'll show you some of the experimental results. So how are we following so far? Okay.
In thinking about the model that had the G that build the representations and then the two parts, where does the backdoor path blocking would be? It has to be in G, right?
Yeah, so let's see. So unfortunately, in this setup, we can't block it. We cannot block the backdoor path in this setup, because the backdoor path can only be blocked. Okay, so for the backdoor path to be blocked, right? So we need to be able to move, the Y and Y prime cannot be conditionally independent given X. So this already doesn't actually agree with the underlying assumption of the generative multitask learning with the unknown confounder. So this one is not going to estimate, let's say, the true causal relationship between X and Y. However, we train it well. I mean, we can get lucky. That's always true, because we are working with a finite number of training samples. We can get lucky, but relying on luck, I heard, is not the best way to do science. I heard that it was in the late 19th century or something like that, but not anymore.
So you will need feedback or something like that.
Sorry?
You will need like a feedback loop from Y prime.
Precisely. So let me actually just go back here. So what we really need is this. So the fact that if we look at both the Y and Y prime, when we're trying to give rise to X, and also the direct a priori relationship between Y and Y prime, we need to look at both of them in order to ensure that how we do multitask learning is going to block this backdoor path that may actually result in a less robust, or the very brittle classifier, and brittle to the potential change in this underlying, let's say, component. Okay. See, this was your choice. You remember, right? So let's see. Okay. Well, we're not done, because the one thing I can tell you very well is the fact that if X is high dimensional or highly structured, doing this is like super difficult. That was the entire, let's say, entirety of my PhD dissertation, trying to use the restricted Boltzmann machines to do so. Completely failed. No one cares about it anymore. No one cares about it anymore. And even now, a lot of people are trying to solve that problem. And then you probably have heard of the series of, let's say, FADs in the, let's say, generative modeling. The latest one is the denoising diffusion model, right? Previous one was a generative adversarial network. One before was a variational autoencoder. One before was there was something called deep Boltzmann machines. One before there was what we call deep belief network. One before that there was a weak sleep network. So many of them, nonstop. But this actually, in principle, cannot really be solved. In any realistic let's say sized problem, that this one cannot be solved. This one just cannot be solved. It's just impossible. But one nice thing is that we are actually talking about supervised learning. So we want to actually infer what y should be given x. So we can just flip the sign using the base rule. And then here, what we can write it down is that instead of trying to maximize the log probability assigned to x given y and y prime, we say that we're going to maximize, jointly y and y prime of maximize jointly over the y and y prime, the log p theta of y and y prime given x minus log p of y and y prime plus log p of x. And this one we don't have to care about. It's just constant with respect to y and y prime. And then what happens is that we get two terms. One is the joint, so a priori joint marginal distribution between y and y prime. And then the first term, which is actually even more interesting, is a usual multitask learning, except for the fact that we don't necessarily assume the independence between y and y prime given x. Although there's no reason why we cannot do that. Anyway, at some point we need to make an approximation, and in order to work with the real world data, and then this is the place where we can now make the assumption that the y and y prime are going to be the conditional independent given x, and that's still fine because the relationship or the statistical dependence between y and y prime will show up from this joint distribution. Yes.
Isn't this exactly counter to the graphical model that you?
Sorry.
Like the graphical model. What it says is given x, y, and y prime are not conditionally independent, right?
Yes, you're perfectly correct. So, but then if we say that, if you ignore this marginal term, right, then making this assumption is going to simply say that, we give up on the generative modeling, and then you have to go for the discriminative modeling. But what we do is we're essentially saying that as if we're going to make some approximation at some point, the place where we're going to make an approximation is on this discriminative modeling portion of the generative modeling portion. So we still continue to have the dependency between y and y prime. The reason why we do that is that just like why this is difficult, this generative modeling is difficult, generative modeling over the y and y prime can be quite difficult. And it's actually more difficult if you have to condition it on a high dimensional vector as well. So what we do is that we're making some decision here on where we're going to make the approximation.
So basically, you could either do, you can either add an assumption on the left term or the right term. But if you make it on the right term, the factorization, then you go back to what we had before, and that's the problem.
Precisely. Yes.
So you did on the left term.
Yes, precisely. And then the reason, in particular, the reason is because this prior is exactly what happens due to this target causing compounder that we don't observe. So it's a kind of a contortion act that we had to go through, but this is what we end up with by trying to figure out the setup under which multitask learning, or a particular variant of instantiation of the multitask learning, has to help. And then now under that setting, what is the realistic and reasonable way to do actual multitask learning? So this is where we end up with. So we're now using, at the end of the day, bringing all the things that we talked about. So we do use a discriminative learning, multitask learning as the first term. But then we introduce this joint marginal between y and y prime that actually tells us about the relationship between the main and auxiliary task. Now, this actually comes back to the earlier point, is that if we chose the y prime, the auxiliary task, so that the auxiliary task is completely independent of main task. That is that the z was not there. Then we just go to the generative multitask learning, and then there is no way we can say that the multitask learning is going to be helpful. So what this tells us is that when is multitask learning helpful? When there is a marginal relationship between the main and auxiliary task. And to benefit from that, we need to follow this generative paradigm and then trying to take into account this marginal dependency between y and y prime in inference test time. So that's actually pretty far away from the original, let's say, discriminative multitask learning, where we assume that the y and y prime are conditionally independent given x, and we use only the y prime, the auxiliary task during training, and then throw away the auxiliary task during testing. So we always carry all these tasks together in our case. Now there's a one sad thing is that so this is where the causality and the predictability kind of diverge away from each other. So let's just imagine one kind of, let's say, scenario. Let's say, let's put it in this way. So the wiper in a car, right? So the wiper in a car. So when do you use wipers? When it rains or when it snows. Let's say it rains, right? So then you have the relationship between the wiper on and then raining is extremely correlational. So they happen almost always. Now, let's say we all live in New York City, at least for this summer, right? Okay, we all live in New York City. And I want to make a perfect predictor to detect whether wiper is on or not, right? In New York City. I have two ways to go about. I'm going to actually look at a car and then see whether the wiper is on and then say that, okay, wiper is on or not. Or I'm going to actually just have an API call to AccuWeather app and then ask whether it is raining or not. And if it is raining, I'm going to say, okay, the wiper must be on. This predictor is going to be like pretty much perfect. But then let's say somehow you decided to go live in Arizona during this summer. Horrible move, but still you did it. It never rains. But some people are going to randomly make a mistake of turning on the wiper. Your predictor is completely failing because it never rains. It's always going to say wiper is always off, and then there's going to be always a chance that the wiper is randomly on. So your classifier is making actually zero prediction of the correct wiper on. But then the thing is, causally, that's correct. We want to look at the actual wiper and then see if it moves and then make a prediction of whether it's moving or not. But in terms of predictability, and then if we can assume that the environment doesn't change, that is, being in New York doesn't change, and we never move outside New York, prediction-wise, it's actually perfect. Just look at whether it's rain or not, and then you say that, oh, it's raining, wiper on. Right? So what that means is that the causally correct model does not necessarily imply that it's actually better at prediction. And in particular, if we can assume that the underlying environment doesn't change between training and test time, we actually do want to use all the correlational relationships, correlations that exist in the training set in order to solve for the test examples as well. And it turned out that that's actually true, in particular when we think about the generalization of machine learning as well. So if the what our model tells us is that okay, we have this actual causal relationship part between the y prime and x. And then what we want is that we want to subtract out this relationship between y and y prime that is independent of the input x. So we wanted to subtract out. That's what our generative multitask learner actually told us to do so. And that makes sense because what this says is that, so we don't know what's going to happen with this z, the unknown compounder. So if we don't know what's going to happen with z, then what is the most robust or the invariant thing we can do is that we say that, we want to make a classifier that's going to be entirely not reliant on Z. And then that is why we're going to remove this marginal dependency between y and y prime. But then if the Z actually is going to be maintained, the distribution over Z, the a priori distribution over Z is going to be maintained between training and test time, there's absolutely no reason why I wouldn't use it. Using that information, the relationship between y and y prime, in fact, may give us a better predictive power of what's going to happen in the test time, right? So the robustness cannot come without any trade-off either. So we can get a robustness predictor, but the robust predictor may actually be slightly worse in this kind of narrow setup. For instance, in this case, where the prior distribution over Z is perfectly maintained between training and test time. So what we, in practice, what we need to do is to introduce this coefficient alpha. When that alpha is 0, that's the usual, let's say, generative multitask learner that we talked about in the previous slide. But we can now increase alpha values so that if we go all the way, if alpha is 1, that's going to be that one. If alpha is somewhere between 0 and 1, we are essentially assuming that the training target marginal, so the distribution between y and y prime during the training time is somewhat beneficial for the test time as well. So that's the degree of our belief. Now, that's the unfortunate thing about this alpha or any kind of research on distributional shift is that you actually, in principle, cannot do anything. If you don't assume how the distribution is going to shift, there's absolutely no way you can do, because you can always come up with a shift that's going to, let's say, make your algorithm work infinitely worse. Right? So we can't do much about it, but the alpha is going to be the value that we choose to represent our belief about what's going to happen in the test. Following? Yes. So predictability, the causality, two different things. Right? Because the reason why I emphasize is that every student of mine at NYU, whenever they watch whatever the talk or the panel where the Judea Per is, they come back and they say that the prediction is that it's all about causal machine learning or causal inference. And then that's actually not true. Causal relationship, very interesting, very nice, but that's not really the everything, unfortunately. All right, so let's just look at it from how it differs. So at the end of the day, this is what we think we need to do in this particular setup. And then this is different from the discriminative multitask learning in a sense that if we ignore these two terms, then we end up with the discriminative multitask learning. So there are two components essentially compared to the original discriminative multitask learning. In terms of the inference, is that we now take into account the y prime as well. And also that y prime's influence comes from two different terms. One is how well that y prime explains this x observation, and how that y prime is related to y itself. So we always consider them jointly. And if we compare it against the generative multitask learning, the main difference is that whether we assume that the marginally py and py prime, marginally whether a priori y and y prime are independent of each other, versus whether the y and y prime a priori are going to be dependent on each other because of this existence of the unobserved target causing compounder z, which we marginalize, and then suddenly the relationship between y and y prime appears. And one really interesting thing is it goes completely against what everyone has been assuming or presuming with multitask learning, is that in this setup, there's absolutely no reason why we actually have to use a single neural net to model, predict y and y prime. We can actually have just two separate neural networks that are trained independently of each other in order to map from x to y and then x to y prime. That's perfectly fine. We're going to train, let's say, f and then f prime to compute these two terms. And then all we need is another generative model or the density estimation model that's going to model the relationship between y and y prime independent of x. And then by combining these three terms together and then doing the joint optimization of the y and y prime, we suddenly get a multitask learner that should work, regardless of how complicated you build this kind of, let's say, neural net in the middle. So that's really quite interesting. It's quite interesting. Yes. I'll show you an idea how it works. Question or?
Well, I was scratching my head.
Oh, okay,
because I
okay,
can't
yeah.
do a question.
All right, sure, yes.
So don't you need another model here for the joint distribution?
Yep. So we do need a model for this joint distribution. And if the y and y prime are very high dimensional or very structured, then we haven't actually tested it because, as I said earlier, learning that itself is going to be challenging. Although learning that cannot be more challenging than actually learning how to generate the y given x. So in a sense that we do have a kind of threefold, let's say, increase in the computational cost or the complexity. However, if you're working with classification problem, where the y and y prime are often just categorical distribution, and in experiments we're going to just use a binary y and a binary y prime. There we can just make a cake and then do some regularization of it to make it smooth it out. So that's the third point. And then this approach should help. Let's see how it helps. And it helps in robustness, right? Helps in robustness. All right. So we just run some experiments, and then this is the issue with any kind of, let's say, experiments where they try to test with the distributional shift, is that there are no natural data you can use to induce the nice natural distributional shift, in particular in the target space. So what we did was we simulated a multitask learning with the simulated distributional shift. So we start with the two data sets with many labels. So it's going to be multi-label data sets. We use the attributes of people data set, which actually tells us about what kind of things that person is wearing in a picture. And then taxonomy data set that actually describes the indoor scene. So what kind of room that it is, what kind of furniture there are, and so on. So one example is this one from the taxonomy data set. The image is of some living room with a view of the kitchen. And then it has a label such as a living room. So this is positive on the living room, positive on kitchen, positive on web bar, positive on, let's say, couch, but it's going to be negative on roof top, for instance. And we get the similar thing with the attributes of people. And then you can kind of imagine how these tasks, if you consider each and every label as a separate task, are related to each other marginally. If it's a living room, then it's very likely that there's going to be a couch. Not perfectly so, but there is a marginal that is, without looking at an actual image, we know that there are some statistical dependencies among all these labels. If it's kitchen, then we know that we very well know that there are going to be dishes, very likely. And similar thing with the attributes of people as well. So for instance, if we chose whether a person is wearing long sleeves or not, and then whether the person is wearing long pants or not, so y and y prime as the two targets, we know a priori, without looking at an image, that they are likely to be both positive. Right? What will be this kind of target causing unobserved compounder here? It's going to be temperature. If it's low, then it's likely that both y and y prime are going to be positive. If it's high, then they are both likely to be very negative. So we can now create all these, let's say, random pairs in order to create many different, let's say, multitask learning problems in order to test our algorithm. And then we did it using only two tasks at a time, and then with the many combinations, just to see that what is the variance we would get across different tasks. It turned out the variance was actually not too large. Now yet another challenge is how to simulate this kind of distributional shift in the y prime and the joint distribution. So it's not really easy to simulate the distributional shift because that actually requires us to collect more data, right? As we change the y and y prime, we're going to collect more data, but that's too much. So we use importance sampling to simulate what would happen, or what would happen to our accuracy had the target distribution been this Q rather than the P distribution based on the data. And we had to come up with some, let's say, heuristics to ensure that this target distribution corresponds to one where the label ranking changes.
because you can't really simply say that well, I'm going to change the probability little by little, and then I'm going to measure the KL divergence to see how far I am, because it's very possible that it started from, let's say, 0.9 and 0.1, and then moved all the way to 0.51 and then 0.49, and still the label ranking hasn't changed, so that the accuracy-wise, any model that just simply says that they won is always going to be correct. So we had to ensure that this kind of shift induces a change in the labeling itself. And in order to even measure that, we couldn't use any of those divergence metric that is overly reliant on the probability numbers itself, but rather on the ranking. So that's why we use the Kendall tau, or this variant that is weighted Kendall tau. And as I said earlier, and then the one thing that is interesting is that when we think about trying to for whatever the problems that you want to solve, we tend to kind of, let's say, combine everything: inference algorithm, or the prediction algorithm, learning algorithm, and how we parameterize the whole thing, mush it all together. And you probably have said it. I say it myself. The people say it is that I use UNet to solve problem A. And I'm like, okay, but how did you use UNet? How did you train this unit? How did you actually do the inference on this unit and so on? Well, because the combination can be however you want. You can use UNet and do the multitask learning with, let's say, generative multitask learning, and then do something else. Or you can use, let's say, UNet as part of the building a variation or encoder if you want. You can use UNet as a part of building a policy for the, let's say, policy gradient algorithm with certain type of exploration policies and so on, right? So here, and in this kind of work, and then what I'm showing you today is where we focus very much on how the learning algorithm or the learning criterion and then inference criterion. And in fact, the funny thing is that I haven't even talked about how we're going to solve these optimization problems, because just by default, I was assuming that we were going to use stochastic gradient descent for learning, and then simple, let's say, exact search or the exhaustive search in the case of the inference in our case. But then what was missing was how are we going to build this kind of neural network machine learning model to compute all those distributions that are needed to compute these objective functions. And then for that, I didn't talk about it too much because we can use anything. So for instance, no parameter sharing MPS is going to correspond to just having two separate classifiers going from the X to Y and the X to Y prime. And then, as I said earlier, it's perfectly fine to do multitask learning with the two single task learners, as long as we combine them in a very particular way that we talked about. And we could just test with the shared trunk network is the one that we talked at the very beginning. That's what everyone does. And then cross-stitched network is some complicated way to build the multitask learning network that I really never understood why it's important. Although Ishan, the first author, he's amazing, so I trust his judgment, but I don't know why this should be beneficial. But anyway, we just wanted to try all three of these out. And then one thing we know is that the layer two shared trunk network and the cross-stitch network, they do work as well as having single task learners. Just when we train them with the discriminative multitask learning. So how do we actually test it when we actually don't know how to set the optimal alpha? That's a sad thing, because finding the optimal, even approximately the value of the alpha, assumes that we know what the target distribution is going to be. But the whole assumption behind the distributionally shift robust classifier is that the classifier is going to be robust to any kind of distributional shift. So before going into how we choose alpha, which is going to be a bit of a heuristics anyway, we decided to look at whether this true optimal value, because we have an oracle, right? We have the actual labels for the test distribution and what the test set is. So we looked at whether the optimal alpha increases as we increase the distributional shift. So if this whole, let's say, framework makes sense, then this alpha value should go from 0
0 to 1. So 0 is where we're going to just the discriminative multitask learning. 0 to 1, of course, it's a bit different because we look at the both of them, but 0 to 1, as the distribution moves further and further away from the original training distribution. And then what we see is that it actually monotonically increases as how the distributional shift actually increases. And it actually happens for all three different types of the multitask learners that we build. Pretty is kind of expected because that's how we build the entire, let's say, framework. This, as we talked about, this multitask learner, this generative multitask learner with the unobserved, let's say, target causing compounder is provably beneficial. So it should have happened. And then we just ran experiments and then yes, it did happen. So that was okay, yes. And then you had the one thing is that of course, you had the optimal alpha. Does that actually mean that we are solving the problem better, right? So whether the accuracy goes up as well. Now, because there is a distributional shift, accuracy generally goes down. In particular, the discriminative multitask learner or the multitask learner that doesn't take into account this P of y prime does drop quite dramatically. So what we see is that what we're trying to look at is that relatively to the dropping accuracy, how much improvements we can get. And then what we see is that again, as anticipated, that we get bigger and bigger boost as the distributional shift gets bigger and bigger. And then again, it holds for all three different types of the learners we have. And we, because all the reviewers were very complaining about the inability for us to give them the solution how to choose alpha. And we told them, we don't know how to do that, but they weren't too convinced by my inability. So we're like, okay, can we actually come up with some, let's say, heuristics that we can use without assuming that we know that the distributional shift is going to happen. So what we do is that we essentially choose alpha to be the greatest value. So we're going to maximize the alpha such that the tested accuracy without any distributional shift. So on the original tested is going to be maintained above certain threshold. So we're going to give the budget of how much drop in the accuracy we are going to tolerate on the in-domain tested. And then that's going to be, these are the budget, the budget of let's say we allow -1%, the -2% absolute accuracy. And then what we see is that yes, if we give some budget without any distributional shift, we lose a bit, let's say 1%, 2%. But as the shift grows, if you use that particular alpha value, then we see that this classifier, this multitask classifier, is indeed more robust than not taking into account this the target causing compounder. So to summarize, it turned out there does exist a very clear setup in which multitask learning can be and is, as we have seen empirically, provably beneficial. And multitask learning in this particular case mitigates the effect of target causing confounders and the backdoor path that is generated or that appears due to the target causing compounder. However, what we have also seen is that in this setup, we have to approach the multitask learning from a very particular angle so that we end up with a multitask learner that can benefit from this particular setup. So what is the kind of next thing? So there are actually many paradigms in machine learning that are used in practice and also work well in practice, but for which we do not know when nor how they should work well. So we talked about the multitask learning today, but another example would be multimodal learning. When should it work well? When should we expect it not to work well? And if it's going to work well, what is the right way to approach this problem? Continual learning, that's sometimes people call it as a lifelong learning or never-ending learning and whatnot. There as well, we often just make up the problem, all those benchmarks, the tasks are changing and so on, but often how the task change, the dynamics is just random. It's a uniform random. And I was like, okay, who cares about that, right? So there has to be some setup where the task dynamics is realistic and interesting, and also is the one that can be benefited if we approach the continual learning in the right approach. Pre-training and fine-tuning, this is what everyone does these days, right? So we pre-train let's say, language model with a large amount of data. and then we fine tune it on the target data, small amount of data, and it works amazingly well. Great, I love that idea. I was actually one of the kind of, let's say, only contributor to the whole idea and everything. But then, when does it help? When should we expect that this pre-training followed by fine-tuning is going to work? We actually don't know. We just do it, and then if it works, great. I'm going to the Hugging Face model help so that every other people can try it out. But we actually don't know a priori by just looking at the problem itself whether it should work or it shouldn't work. And indeed, Sam Bowman at NYU has been testing a lot with is there a particular order in which the pre-training or the fine-tuning should be done? Is there any particular set of the source tasks that are going to be helpful for a particular set of the target tasks? Here are like tons of experiments over the, let's say, past 5 years. And then answer so far is that no, there's no pattern. But there has to be a pattern because it's not magic. So there has to be a pattern. So all these paradigms, we use it, they work well. Certain scenarios, we don't know exactly when they work well. So we need to be able to come up with a setting that is both realistic, because you can always come up with some toy setup that doesn't make any sense where these things work well. So realistic and still can guide us in determining whether any given problem can benefit from any of these paradigms. And the second thing is that this work, what we actually realized was that hold on, the multitask learning is inherently a statistical problem. There is a reason why Rich Caruana was pointing out all those statistical data amplification and whatnot. But it turned out to give a setup in which multitask learning can help work well, we could actually use the idea, some of the concepts from the causal inference. And that actually does tell us that in order to think of where these statistical algorithms are going to work well, we have to actually go beyond the statistical perspective alone in order to provide a context. So, that actually does raise a question: what other perspectives can we use to explain other paradigms and use cases in machine learning? I don't think quantum mechanics is an answer here, unfortunately, although quite a lot of people actually trying to look into it. But yes, and that actually does, finish this lecture. If there's any other questions, let's talk about that a bit further. Clear, right? Yeah. Nothing left to ask.
You said 25 minutes, more or less.
Oh yeah, that's true. Let's see. What's the time? Oh, did I actually spend the entire hour and a half almost? Oh, okay. So probably I gave this talk in front of another audience last week, but there was 25 minutes, and then I somehow made it in 25 minutes. So no one there probably understood anything. But yeah, but glad to have you all here. I'll be around, and then my office at NYU is about 10 minutes on foot from here, and also I'm working at a Genentech precision design team, which is also office is about 5 minutes or 7 minutes away from here. So if you want to discuss anything further about the machine learning like science or anything about the career path, because I used to work at Facebook, many of my PhD students are at all those tech companies as well. So if you're interested in those, how the career path in tech companies look like, just do let me know. And also if you're going on the job market soon, and if you're interested in drug discovery, also do ping me, and I'll be able to meet in person for coffee or something like that for discussion. All right, I guess that concludes it. Thank you.
We are going back to the second floor.